let me just maybe give the intro for the next lecture. Yeah. Maybe we don't have enough time to finish the whole thing. Okay. So we just see how to use the basic cut matching game without deletion and transferring vector, right, to find sparse cut. Now we're gonna try to solve expanding balance separator fast. Okay. So let me recall you we said that F is a balance separator. If once you remove F from the graph, then every component has at most half vertices, half two vertices. And what we're gonna do is this. Given any graph, right, we're gonna find, we can just find this flow expanding balance separator. So we have seen the algorithm, the slow algorithm that, one sec. Good, okay. We have seen the slow algorithm that give you something like 1/4 cut expanding balance separator. But today we're gonna just get a bit worse. But it's gonna be fast. Okay. It's gonna take something like log cube calls to MaxFlow. Okay. If we can compute, so this is really just expanding balance separator, and if we can compute it fast, then you recall how we get SE hierarchy in this time. How can we do that?
Just keep calling it recursively.
Exactly. Yeah. We get the balance separator that is expanding. This would be EL, like the separator at the top level. Just recurse on each of the components. You need to recurse log n levels. So the total running time here, just this thing times log n. Times log n. You get this. Okay. So if we can do this fast, then we get separator expanding hierarchy fast. Okay. Okay. And what I'm gonna do, so this is our goal. Okay. And to do this, I will kind of work with split graph. So split graph is some simple thing. It's really just, I said that the graph G prime is a split graph of G. If for each edge of G, I split it into two nodes. I add, for this edge, I split it into two edge and add some node in between. That's it, nothing. Yeah. Okay. And now in this split graph G prime, given any edge set, if I choose this and this, then I can look at split node, corresponding split node. This is F, this would be SF. Okay. So for any edge set in G, I can take the split node corresponding to F. Okay. That would be F of F, S of F. Okay. And so you can see that G prime is just the same graph where it's just this graph, and I just gonna say that the vertex set of G prime is original vertex set and the split node for every edge.
Are there capacity on the edges? Like, if so, like, what's
Good.
the new capacity?
So let's say that the capacity is 10, then we set 10 and 10. Yeah. But like in this lecture note, I just think of unit capacity, but yeah, it just works in this way to capacitor graph. So now, one thing that I want you to convince yourself is that if this split nodes, indicator of the split node, SF, is expanding in the graph G prime, then the edge, or in other words, the degree of F, would be expanding in G. This is really extremely intuitive, but like it needs some small proof. But because the way you think of this is just like you can send flow between any edge in F anyway, and this is just I literally just like put some node in each edge and say that I can send flow between this node in G prime with low congestion. Okay. So, but I will not prove this. Convince yourself that it's true. But if this is true, then it means that it's enough for me to just do this. If I want an expanding balance separator, I just need to find a balance separator. And I need that if I look at the split node corresponding to F, this thing is expanding in the split graph G prime. Because this just means that F is expanding in G. Okay. And phi here, this phi is going to be something like log over 1 over log square. So this is 1 over log square. Okay. So that's a setup. Like this is my goal now. Okay, I want to find F such that first of all F is a balance separator in G, and if you look at the split node corresponding to F, it's expanding in G prime. Okay. And here's a key subroutine, which we will try to do. It's basically gonna expand, say that your node weighting is expanding or it shrinks your node weighting. So it does the following. Suppose that I start with some balance separator. Like I give you some initial balance separator, F naught. And this algorithm, expand or shrink, will find another balance separator, F. Okay. And this F will either be expanding,
Yes.
or it would shrink. It would shrink, like it is smaller than F naught by some significant factor, like reduced by a constant factor. And the total time is like we're gonna call like log square max flow, which is basically from cut machine game, and this running time from the cut player. Okay. So why, if we have this, why are we done? Why does it imply the main theorem?
Just keep doing 2.1.
Yeah.
It cannot shrink like more than log n times.
Exactly. Yeah. Like we just kind of initialize your F naught to be the whole edge set, right? If you start with this thing, F naught is just a balance separator. Trivially, it split everything into one component, a component of size 1. So start with that. And feed this F0 to expand or shrink. And this guy will just return some balance separator that is already expanding. If that's the case, if it's expand case, you are done. You just return. Okay. But otherwise, you would get a new balance separator which is smaller. And this new balance separator, just feed it again to expand or shrink. And this can repeat at most log n times. So yeah, so if you get expand case, you're done. If you get shrink case, you can repeat log n times. Okay, good. So that's the goal, and maybe to do this, we will just basically use cut matching game where we can delete things and we can transfer vectors. Okay. I don't think I have enough time, 10 minutes. So let me just describe the algorithm and we analyze it next time. Okay. The algorithm is here. Again, we kind of initialize the graph X, okay, for the cut player. Okay. The cut player have a graph where its vertex set is it's a split node for every edge in F node. And then we repeat for log square round. In each round, we do something like cut matching game. So maybe I draw instead of going through this. Yeah. Okay. So the input is the graph and some balance separator. Okay. So it's like you have a graph, and maybe this is your balance separator. This is like maybe yeah. Okay. And then the graph X is literally just split node on each of this guy, on the red guys. It's split node on this thing. You know, like each node of this corresponds to each edge here. Okay. And then in each round, well, the cut player will look at the graph X and then choose A and B in here. Choose A here, and maybe here. A is going to be small, like there's going to be like some, there's going to be active set, like the guys that you didn't delete yet. So you choose A and B in the actives, inside the active one. A is going to be small, B is going to be big. Okay. And so we just kind of look at the corresponding, maybe this is kind of A, and this maybe is B. Like this thing. Okay. And what we do, just try to send flow, because the whole goal of the cut matching game is to find matching from A to B, which means like you kind of want to send flow from A to B. so that you can find a meshing that is routed by the flow. So try to send flow. So compute flow and cut in this graph where like you have, you know, the node weighting, which is like something like A, and the source is A and the sink is BI. It should be actually from the split. You do it in the split graph where the source is the split node. Like you try to send one from the split node of AI, and the sink is all one from the split node of BI. And now you might get, if you get the meshing, you're good, but you might not get it. You might get a bottleneck. Okay, so the bottleneck might look like here. Meaning that maybe this guy, let's say like there are a lot of guys here, and you have the cut here of size 1, of size 2. So what happened is that you know that this guy can send some flow to here. The guy is, this is like, think of this as Li, right? Everything that is not cut, you can send flow. So this guy can send flow to something in B. The cut edge here, like the source here can send flow to the cut, but not everyone can send flow to the cut. It got stuck. But from the cut, there is a flow to some BI. Okay. So what we're gonna do is that we're just gonna say that we're gonna update your F. Like this is, maybe you think of this now as, actually this is F I-1. Your new F is gonna be this thing. You add this to your F, and you remove all these things. So you see that, like, it just defines a new balance separator. Suppose that this side is less than n over 2. Then you just get a new balance separator. Okay, and now we're just gonna define a meshing. Okay, so well, this basically we're gonna transfer, like you have this guy to this and to this. You're gonna transfer vector from like the source that can be sent to the cut, that can send flow to the cut. You transfer the vector to the cut, to the edge in the cut. And now everything on this thing can send flow. Like this is now your new this is now kind of your new set A, and kind of this set A prime, the new set A, can send flow to B. Okay, and like the guys that used to be in F in the separator, but you cannot send flow. This guy is the one that you cannot delete, because it cannot send any flow, so you just delete it. Okay, so that's kind of the sketch of what's going on, and we're gonna make this precise next time. Yeah, but
A and B, like they only contain the new split vertices, or
yeah. Like actually, like the active set here is gonna be exactly, maybe active set T-1. It's gonna be exactly your it's just gonna correspond to your separator, balance separator at route I-1.
Oh.
So the active set will correspond to your current balance separator. And and you see that some of the balance separator is removed, so we need to delete. And some actually can send flow, but we add some new guy. So this guy need to obtain some vector from the previous guy. So what we do is just any previous, any cut edge, any separator edge that is cut out will kind of transfer the vector to the new separator. Okay, that's the idea. We're gonna go through this carefully next time, and but I hope from here you see where deletion and transfer vector is needed. Okay, yeah, see you next time.